hope we will all enjoy your presentation, Costas.
Let's hope so.
So let's
Thank
wait
you. Thank you so much.
3 minutes to get more people.
Okay.
Yeah, no problem. We can wait 2 minutes.
Right now we have 31 attendee.
That's not bad.
Normally we start at 5, but if you'd like, we can wait 2 minutes. There is no problem.
Yeah, I have time, so no problem. Yeah, I can see here the participants.
Yes.
And if there are questions, we can they can ask both by chat or by opening their microphones. It's up to you how to organize this.
Yes, Hadi will manage it.
Okay.
Yeah, normally they already know that if anyone has any question, they can raise their hands and they write it in the chat box. So we can, for a better communication. Dr. Abdullah, you need to say something, or you're just trying the option? Oh, okay, he was just trying.
I'm just trying.
Yeah, no problem.
Good.
So a few seconds and we can start.
Yeah. I'm waiting for you.
Hello, Dr. Rabia.
Welcome, Dr. Rabia.
Hello. How are you?
Very good.
Fine.
Well, Doctor.
We can't hear you, Dr. Rabia. So I guess we can start now.
I guess I have a connection problem. Welcome, everyone.
Thank you.
Okay, thank you. So Dr. Rabia is saying welcome to everyone. He has a problem in his internet connection. So I guess we can start our event now. So hello, everyone. I hope you're doing good. I'm going to present myself. My name is Hadi Albid, IEEE LIU Student Branch Chair. Today's event is Voltage Stability Webinar. It's an event in collaboration with IEEE Power Chapter in Lebanon, where our IEEE distinguished lecturer will explain the voltage stability concept, which is a term related to power domain. Today's speaker is Mr. Kostas Vournas. Mr. Vournas is a professor emeritus in the School of Electrical and Computer Engineering of National Technical University of Athens, Greece. He has published close to 200 papers in international journals and conferences and has co-authored the book Voltage Stability of Electric Power Systems. His research interests are in the area of power system dynamics, stability, and power and control, and include the voltage stability and security analysis, wind generator and the integration in power systems, novel control applications, and the distribution and transmission grid, as well as the effect of deregulation on power system operation and control. He is fellow of IEEE since 2005, life fellow since 2019, member of CIGRE, editor of Electrical Power System Research International Journal. He has the recent of the IEEE PS Prabha Kundur, sorry for the pronunciation, award for 2019. He was chair of the IEEE PS Power Tech Steering Committee 2007 till 2019. Region 8 representative on the IEEE Power and Energy Society, PES, Governing Board 2011 till 2014, and is the immediate past chair of the IEEE PS Power Systems Dynamic Performance Committee. Since 2021, he is chair of the Energy the IEEE European Public Policy Committee To welcome more our speaker, I'd like to invite the Vice Chair of IEEE Power Chapter in Lebanon, Dr. Muhammad Arnaout. Dr. Muhammad, the screen is yours.
Thank you, Hadi, and thank you for this to organize this webinar. So thank you very much, Professor Costas, for accepting our invitation and sharing with us your great work related to the voltage stability in power system. I would like to thanks also the attendees across Lebanon and maybe abroad. And on behalf of IEEE chapter, we are very glad to joining us, especially during this hard period faced in our country. And we look forward to return back very soon to the normal situation, inshallah. Professor Costas, the floor is yours, and thank you again in advance.
Thank you very much for the nice introduction and for the invitation. As I said before, I'll say it now officially, I'll be glad to visit you when time and the
constraints will be
will allow. Let me just try to bring my screen back. PowerPoint, yes, it's allow. And now I think you can see my slides.
Yes, we can.
Yes.
Okay. Okay, so let me just get out the pointer. So the discussion today is to make a short introduction to voltage stability of electric power systems. This is a large topic, so only very few things I'll be able to say to describe this this field. And then I will let anyone that is interested to look either at textbooks or papers. And I should say at this point that this presentation is based on the book Voltage Stability of Electric Power Systems, which I have co-authored with Professor Thierry Van Cutsem from Belgium. And the outline of my presentation today will be first an overview of power system stability and its classification, then how the voltage stability problem is related to maximum power transfer, the importance of generator, and if you have a system with power electronic converters, also of converter reactive power limits. The main item that we'll discuss is creating voltage stability is load dynamics, so I will focus on load dynamics, and there are fast and slow response. And this, as you will see, is the whole classification of stability in power systems, and voltage stability in particular is in fast and slow time scales. I will say a few things about the load tap changers that are controlling the distribution side voltage of bulk power delivery substations. Then the technique known as quasi-steady state simulation. And I will just touch on items that are, let's say, one step further, which is voltage stability monitoring and protection against voltage stability, voltage security assessment, and voltage stability support that you can get from distributed resources. If there are questions on any of these topics, you can ask me at the end of the presentation. I'll be happy to give more details. So in terms of power system dynamics,
Raise your hands.
Yes, please. Was there a question or?
They can raise their hands to ask any question they want.
Yeah, so it's okay. You can hear me. You can see the slides. Everything fine?
Yes, yes, yes.
Okay. Okay, so the dynamics of power systems evolve in different time scales. The fastest one that we consider is the electromagnetic transient, and power electronic converters also act in the same time scale. And this is in the sub-period, by speaking of 50 Hertz alternating current, the period is 20 milliseconds. So whatever is faster than that and have a time constant of 1 millisecond or even less are called electromagnetic transient, and these are modeled using the electromagnetic transient program. However, most of the stability-related issues evolve in a slower time scale of synchronous and induction machine electrical and mechanical transients, which is in the area of 1 to 10 seconds, and we tend to call this time frame as short-term time frame for stability. And the slower time frame, where we have load and other slow dynamics, we call long-term time frame. And this is a time scale that goes from several seconds to several minutes. And this is the time frame where we have frequency and voltage stability issues, as I will explain in a minute. So you see, the power system is a multi-time scale system, and it is very important to know which time scale you are interested for a specific application. I will just want to refer you to two recent documents that were published by the Task Force on Stability Classification of Power System Dynamic Performance Committee of IEEE. And these are the paper on IEEE transactions on power system, which is available online, which is definition and classification of power system stability, revisited and extended, and the technical report, which if you are PES members, you can download from the Resource Center of Power Energy Society, which is stability definitions and characterization of dynamic behavior in systems with high penetration of power electronic interface technologies. The paper is an update of the older classification of power system stability and is, let's say, a short version of the report. So if you have access to either the paper or the report, you know all the recent changes in classification of power system stability as let's say, classified by IEEE Power and Energy Society, and in particular the Power System Dynamic Performance Committee. So the classification from the older report, which was a joint IEEE and SIGRE report, we classify three different types of stability: rotor angle stability, frequency stability, and voltage stability. In the new report, you see that there are two other classes of stability problems, the ones related to resonance and the other related to interactions, fast and slow interactions involving power electronic converters. I will not refer to these because we are interested in voltage stability. And voltage stability refers to the ability to maintain voltages, and is different from frequency stability, which is the ability to maintain frequency close to nominal value, and different from rotor angle stability, which is related to maintaining synchronism between generators. So assuming that all generators are in synchronism, and assuming that we have a global balance between active power generation and active power load, by global we mean in the whole system we have enough power from the generators to feed the loads. In voltage stability, we are interested in the ability of the combined transmission and generation system to deliver the power requested by loads. So we have the power at the generation. The problem is if we can transmit this power to the loads. So the voltage stability is load driven, whereas the rotor angle stability is generator driven. And we have two types of voltage stability: long-term voltage stability, on which I will refer most of the time, which has to do with slow load dynamics, and short-term voltage stability, which is mostly related to fast-acting load components, typically induction machines. So voltage stability is how we keep voltages in the power system, but it has to do with the ability of the transmission system to transmit the power from generation to loads, and it's load dynamics that drive voltage stability. So if I want to put an answer to the simple question, what is voltage stability? I will take the answer from the book of Professor Thierry Van Cutsem and myself that I mentioned in the first slide. Voltage stability stems from the attempt of load dynamics to restore power consumption beyond the capability of the combined transmission and generation system. So you see there are several aspects in this definition, which one of which is that there is a maximum power transfer, and this maximum power transfer limit is set by transmission and generation combined, and voltage instability is load driven. It is the loads that tend to consume more power than the maximum that create the instability.
Professor, sorry.
Yes, please.
Sorry. In your presentation, you are display only the slide, the first slide. We have only the first slide. I don't know if you are in the first slide or in other slides.
No, I'm in slide 5, but I don't see if I let me see.
Now, yeah. But
now you see slide 5?
Yes, if it's possible to put it at full screen, please.
Yes. But now you see it or not?
Now, yes. Slide 5, but it's not on full screen.
It's not on full screen.
Yeah.
The
Sorry for this
PowerPoint
interruption.
window.
No, it's
the
okay.
other slides on the side.
We have to find a solution to this. So, so now you see the slide.
The screen.
Do you see this slide now?
Slide 5, but not in full screen.
Okay. And now do you see slide on full screen?
Not yet.
How can I? So in this, if I put it like this, you can see the presentation now?
Yes, we see the presentation, but each time, please make sure to do the step in order to have the slide
Right
6, 7, and 7.
Okay, so this was what I was presenting. You can see
Yes.
now slide 4.
Yes. Your screen, doctor.
Pardon? You said something I could not follow. Now, can you see?
Screen. There is a button that can take us to the full screen.
Yeah, now I see my full screen. Do you see the full screen? No. Oh. can I do this?
No, no.
Okay, let me do it differently then. Just a minute. I'll put my full screen. So you will see what I will see. And now, can you see slide 4, please?
I think it's fine. It's okay now.
You see slide 4?
You can
Yes.
continue.
You can continue, please, but you can go to slide 5 in order to testing if it's okay or not, please.
But right now you see slide 4, right?
Yes, yes.
So this is the slide that I was discussing before and you could not see it. The 3 types of, let's say, traditional stability, and we refer to voltage stability. And you see here it is load driven, and we have the short term and the long term. And as I said, the definition of voltage instability refers to the maximum power transfer voltage stability is load driven in the sense that load is trying to consume more power than can be transferred, and it is a dynamic phenomenon because it's the load dynamics that drive the stability. And as you know, when we speak about stability, we assume some type of dynamics that become unstable. But even though it's a dynamic phenomenon, we can use static tools which correspond to equilibrium conditions. Okay? So as for the reactive power, because voltage stability is many times related to reactive power, I want to point that there is a strong influence by reactive power, but the stability limit is affected by both active and reactive power. Okay, so I'm going to give you a DC example. Can you see slide 6 now, please?
Yes, yes, it's fine.
Okay, so I will analyze this very simple problem just to show you what is voltage instability, and then I'll show you roughly the complexity that we have with AC system. But in this case, we use just a simple DC system, battery, series resistance, and resistive load, which we assume it's type of a rheostat. I can change the resistance of the load, RL, to control the power P consumed by the load. So you see this very simple system. I can show you how it can become voltage unstable. First of all, you know the maximum power transfer theorem, which says that if you have resistance of the load, RL, equal to resistance of the line, R, then you have the maximum power that you can transfer from the source to the load. And this maximum power you can easily calculate. We are in DC system, so RL is equal to R, so the current is E over 2R, and the resistance, the power consumed by the resistance is Ri square. So you have E square divided by 4R is your maximum power. So if you put values here, 1 volt, 0.5 ohms, you see that your maximum power is 1 over 2, so it's half a watt, okay? So this very simple system can transfer up to half a watt. I guess you are all familiar with DC, so it is a very simple exercise. But I will make it more interesting by including load dynamics, and I call this load dynamics self-restoring in the sense that the load wants to consume power P0. This is typically if you use electrical heating to heat your room. You have a specific amount of energy that you need to transfer within an hour to keep the room temperature constant. So this is a specific power. So you need to consume power P0 as controlled by your rheostat and by your thermostat. And what you do is you decrease your load resistance to consume more power. So if the power you consume is less than P0, the power you consume is always I squared times RL. RL is varying, so I is varying too. So if you consume less than P0, your R will decrease. And this because by reducing the resistance, you increase the conductance, so you increase the consumption. So in general, in power systems, the loads are considered admittances. So if you have one more load, you have one more admittance, so you have more resistances in parallel. So resistance is getting less when conductance is getting more, and the more conductance you have, you increase the conductance to increase consumption. It's like when you have parallel connection of more consumers, you have a larger load, which means a larger load conductance. And since I use R here as resistance, you have less resistance. So the real question is what happens, because this P0 is, you see, part of a differential equation, but it's an input to the differential equation. It's how much I want to consume. And suppose that you want to consume more than what your maximum transfer, more than your maximum power transfer, what will happen? And what will happen is voltage instability. So you see here that I said that in this simple network, the maximum power is 0.5 watts. And suppose I put a P0 that is slightly larger than 0.5 watts. I start from an initial point where my resistance is such that it consumes 0.1 watt, but I take the P0 to above 0.5 watts. So you see what I changed here is P0. I had an initial P0 of 0.1. I was at equilibrium. RL was constant. Now I increase this to above 0.5, but I get a decreasing resistance. And by decreasing resistance, I initially consume more power. You see, this is power versus time. And at some point, I arrive at the maximum power, and I know the maximum power is when my resistance will be 0.5 ohms, like my line resistance. And at this point, I'll be consuming, the voltage, will be something around 0.5 volts. So I start from 1 volt from the source. I have half the drop at the line, and the other half is 0.5 watts that I take here. And after this maximum, what happens? My resistance decreases more, and by decreasing more, it eventually goes to 0. And when the resistance goes to 0, the voltage goes to 0, and so also the power goes to 0. The current is not infinite because I have the line resistance, so I have short circuit conditions, and I have 0 consumption of power. So you see, even in a simple DC system where there is no reactive power, I have this type of behavior if I ask to consume more than I can consume. So this very simple example is to show you what is voltage stability before going to the actual AC systems. And I will try to make this a bit more detailed. but I will not go into all the detail as I let you do the calculations on your own. What I want to show here is if I have now AC lossless power system, but it's a very small power system with only 2 buses. I have a generator which keeps the generation, the voltage constant to E. I have a speed governor in my generator that always keeps the frequency constant so that the generator consumes the power necessary, produces the power necessary for the load to consume. And my question is, what are now my conditions for power transfer in this very simple network? So if my power is P active power and Q reactive power, you know the formula in AC systems. I assume you know also the per unit system, but you can do it in any other system. The complex power is VI conjugate. V and I are the phasors for voltage and current. And by doing some simple algebra, you can see that the power that you receive at the load is E, the voltage of the source, V, the voltage at the load, divided by X, the reactance of the line. It is a lossless AC line, but it does have a reactance. And sine theta is the angle, theta is between the load voltage and the generator. So this is the voltage, the load voltage angle, theta. So when it is less than the generator angle, when theta is negative, the power that's consumed is positive. This is Q. Now I can take P square, or I can take sine square plus cosine square equal 1 and replace sine by all these. And what I get in this case, by eliminating theta, I get a biquadratic equation. So you see, I can solve for V square, which is the voltage, the load voltage squared. And you see, I have this equation where I have Q and E and P as parameters. And whenever I can solve this equation, I can find what is the voltage for a given P and Q. However, I cannot solve this for all values of P and Q, because in order to have a solution to give me a V square, I must have the discriminant of this biquadratic equation to be positive. And by discriminant, you see, you get discriminant positive, you get this condition here. And this condition I have put in a figure, and not to have P and Q in watts and vars or per unit, I take it as percentage of the short circuit power. And by short circuit power, I mean if I have V equals 0, you see the current is E over X. So the short circuit power in AC system we call E times short circuit current. So E times E divided by X, E squared by X is the short circuit power. So I have the short circuit active, the power as percentage of short circuit, active power as percentage of short circuit power, reactive power as percentage of short circuit power. And you see, if I plot this here in a two-dimensional P and Q axis, I get a parabola. And this parabola gives me the limits where I have a solution to the biquadratic. So inside the parabola, I have two solutions of the equation. So I have two values for V square. Outside the parabola, I have no solutions. And on the parabola, the two solutions become one. Do you follow me up to here? Are you all seeing slide 9?
Yes.
Yes.
Okay. So this on the PQ space, that's what we call load space, is the loadability limit or the loadability surface consisting of all points where I find a limit after which I can no longer solve for voltage. So if I take the conditions where I have along this equation, if I take it equal to 0, and I take the condition for a constant power factor. So if I have constant power factor, this means that Q is proportional to P. So I go along this line, angle phi, and the tangent of phi is my power factor. Okay, so cosine of phi is my power factor. So if I take Q and I take P tan phi to replace this, I get one equation equals 0, and this will give me the maximum power, which is a function of E squared by X, which is the short circuit power. It's E squared by 2X, so it's half the short circuit power, times this function of cosine and sine of phi, the same with Q max, when the Q is again P max times tangent of phi, and the voltage where I have the maximum power. It's a bit complicated if I take the power factor, but if I take the simple case where the power factor is 1, which means I have only active power, then the maximum power that I can transfer is half the short circuit power, and the voltage where I have the maximum power transfer is my feeding voltage divided by square root 2. This is roughly 0.7 times my feeding voltage E. And if I take the case where I have no active power, so cosine is 0, I have, of course, no active power in this case, but the maximum reactive power is 1/2 of the short circuit power. So you see this, when I try to, in a lossless AC system, I try to transfer Q, reactive power, then the limit is exactly the same as in the DC system with only resistance. So it is 0.25 times the short circuit power. And the power where I have, the voltage where I have the maximum power transfer is 1/2 of my feeding voltage. So these are some simple formulas. You can plot it in many ways. And this is a 3-dimensional case where I'm plotting the voltage as far as percentage of the feeding voltage. I'm plotting active power P from 0 on, and I'm plotting reactive power, and this is the 0 here, so this is 0 P and Q, and you see you get this type of a solid where you have an equator that is shown here, which is half the parabola I showed in the PQ plane. And for each power factor, for instance, for this curve here, I have one curve, and I can plot, this curve is showing P and Q as a function of V, or V as a function of P for a constant power factor. And I can plot this only in 2 dimensions to make it simpler. So here I have the active power, and here I have the voltage. And if I take, for instance, the 0 angle, which is the unity power factor, you can see that I have a maximum power that's 1/2 of the short circuit power. You see 0.5 here. This is my maximum power. And here is the voltage where I have the maximum power, which is close to 0.7 times the initial feeding voltage V. So I have a whole bunch of PV curves, each for a different power factor or a different tangent of phi. And if I go to negative tangent, which means that load is consuming P but is producing Q, reactive power, I have an over voltage and I increase both the maximum power transfer but also the voltage at which I have my maximum power. So as we'll see, this maximum power will be also the limit of voltage stability. And this is one reason that we need to do very detailed studies for voltage stability, because if we have compensated networks, which means we produce reactive power to increase the power transfer, then what happens is that the voltage where I have the maximum power, which is the voltage stability limit, can be very close to nominal voltage. So keeping the voltage close to nominal does not mean that you are safe from voltage instability. Okay, I think I have spent enough time for this. So I'll go a little bit faster to make the link between maximum power and stability. To do this, I keep again the two-bus system, exactly as I had before. I assume I have a unity power factor, so my tangent phi is 0. I have a constant admittance load because power factor is also 0. This is a constant conductance G. And I assume I have load dynamics with a time constant T. This can be small time constant, then I have a fast load. There can be large time constant, then I have a slow load. And you see G dot, which is the derivative of the load conductance, varies such that if the load consumed, so GV square is the power consumed, P, if GV square is less than what I want to consume, P0, my conductance will increase. It is the same as I showed with the DC system, but now this is an AC system. So what happens is the power consumed is, as I said, is GV squared. And if I do some algebra and V squared is written as a function of E squared, you'll see that it is a nonlinear function that includes G, which is my state variable. And the consumed power is E squared G divided by 1 plus XG squared. So if I want to get the eigenvalue, because this is a scalar system, it's very easy. It's the partial derivative of P with respect to G and divided by V0 and T, of course. And this partial derivative, you know how to take a partial derivative, will be 1 minus xg squared divided by 1 plus xg squared and all of this squared. So you see that for any specific value of G, the eigenvalue, which determines the stability, can be calculated from this formula. And clearly, the eigenvalue is negative as long as xg is less than 1. So the numerator is positive because of the minus in front. The eigenvalue is negative and they have stability. So while g is less than 1 over x, I have stability. When g becomes exactly equal to 1 over x, which is what we call the impedance matching, but now it is the impedance matching in AC systems. I showed to you the impedance matching on the DC system, where the resistance of the line is equal to the resistance of the load. In AC systems, the impedance matching for constant power factor is when the impedance of the load, the magnitude of the impedance of the load is equal to the magnitude of the impedance of the line. So in this case would be 1 over G equal X, or when G is equal to 1 over X, I have impedance matching conditions, I have maximum power conditions, and I also have 0 eigenvalue. So you see that when I arrive to maximum power conditions, the eigenvalue of a dynamical system which tries to consume a specific power P0 becomes 0. So I have an instability condition. After that, if I go to trying to increase my G after G equal to 1 over X, I'll have a negative denominator, I have a positive eigenvalue, so my system will become unstable. So this is, in a very simple system, the relation between voltage stability and maximum power transfer, and this can be generalized in systems with more loads. I will skip a number of slides here. I have sent all the slides just to allow you to have a look. And I want to say a few things. What happens if my source, either a generator or any other source, for instance, a converter, comes to a limit? So to do this, I want to compute from the AC system the Q generated by the source, which is the Q of the load, plus what we call the reactive losses, Xi square. And these are right again as a function of P and QG and E, which is a constant voltage. You see I get an equation here, which I can solve for QG. And you have this here solution, which you can have for different power factors again, because Q, you see, is here, can be, if you have Q equal tangent phi by P, you get a simple one. So you see the normal operation, this is the QG, again as percentage of the short circuit power, and this is P. You see for each P and each power factor, you have a specific consumption of reactive power from the source. For instance, if I'm at 0.4 and I have 0 power factor, I need so much Q. But you see, when I arrive at the maximum, then after that, I cannot, of course, have more power than the maximum. But if I go to the upper part, here it is the unstable condition. My conductance is more than 1 over X. So in this unstable point, I consume more reactive power from the source. So the lower part is the stable part, the upper part is the unstable part, whereas in the case here, the PV curve, the upper part is the stable part, the lower part is the unstable part. Okay, so in this case, I have the power generated by the source. So what happens if this power is limited? So my source does not have enough power to go to the maximum power. For instance, in the case of unity power factor, I don't have 0.5 of the short circuit power, but I have something less than 0.4. So I stop in this line. What happens is that as my load increases, I can go up to this point, but I cannot go beyond, because to go beyond, I need more reactive power. So this is, in this case, the limit. You see the limit now is not where the maximum power unconstrained condition exists. Here I have a maximum power due to the constrained reactive power that I have from the source. So I have a limit that is less than 0.5. And after this limit, again, I have voltage instability. So I'm afraid I have spent more time to describe things. So I don't want to go into too much detail from now on. I will let you see the slides, and I'll jump to say a few things about loads. And as I said, we have short-term voltage stability where we are interested in fast dynamics like the induction motor. And here we have a time constant less than 1 second. And here the dynamic load is the induction motor, and we can assume that the state variable is the motor slip. And in this case, if you are familiar with induction motors, you know that for a given voltage, you have a maximum torque. So again, in the case of the motor, induction motor, the instability condition is when you reach the maximum power, the maximum torque that the induction motor can apply. So if your load torque is more than the maximum torque, then you have voltage instability, and in this case, you have a motor stall. If you go to long-term time scale, then you have slower acting load restoration, and this is done in bulk power system transformers, where you have load tap changers that try to restore the voltage of the distribution side. So if you have loads that are voltage sensitive, then by restoring the voltage at the distribution side, you also restore load power. And these tap changers act with time constants, let's say, of a few seconds, like for instance 5 to 10 seconds. So they are much slower than the generator and motor dynamics. And the equilibrium here is when you have the secondary voltage within deadband. And we have even slower loads, like the thermostatically controlled, which can have time constants of several seconds. I will not go into this. This is what the tap changer will do. This is the distribution transformer. This is a distribution feeder. You see I can have compensation, I have different loads. But if I restore this secondary voltage to its set point, let's say V20, this means that I also restore the active and reactive power consumed here. So I restore the active and reactive power seen at the primary. I will again let you see these slides and do the calculations if you are interested, but I'll just want to show how this tap changer can create an instability problem. I assume again a radial two-bus system. This is P, this is V. This is the PV curve, exactly like I got before from the lossless system. So the maximum power is at point C. And so this is the locus of all the solutions of P. Q is supposed to be a function of P, so I have constant power factor to have a single PV curve. And you see that any consumption of active and reactive power has to be on this PV curve. I have no solutions for P more beyond point C, but if I have power P less than the maximum, you see I have two intersection points, S and U. And on this slide, I'll also show the equilibrium points, which is the intersection of what I call load characteristic. And this load characteristic, as you see, is a constant power load characteristic. P is equal to constant. Because as I said, at equilibrium, because V2 is restored, power is restored to this P0. And in the same, I'll also show the so-called transient load characteristic, which is a parabola, because for each value of R, the power is a function of V2 square. So this dotted line here is the consumption of power for at one specific point of R. And if R increases, you see I have a second value here. So the upper part is stable because if I increase R, which means I decrease the conductance of the load, I have less power. So decreased conductance, less power is okay. So increasing the conductance, I get more power. In the other point here, if I increase the conductance, I get less power. So point U is unstable and point S is stable. So I have two equilibria. The upper part is stable, the lower part is unstable, and I have each type that R moves, I have a transient characteristic and an operating point that depends also on the value of R. Okay, so I think I covered most of what I wanted to say. I will not go into too much other details because time is getting short. I will just leave the QSS. And if I want to just give you an idea of what happens to large power systems, in a large power system, we have a large number of equations. So we have several loads, but we can assume a stress direction that all loads will change with one specific participation factor lambda, and all reactive loads will increase with a participation factor mu, which depends on the lambda. So it is mu times, so this mu is equal to the tangent of phi. And generation also increases with a similar participation factor, but the sum of all participation factors is larger than 1, so that I can cover all loads. Now, with this stress definition, what I can do is I can make a multi-dimensional problem into a single dimension problem. So you see the only thing that I vary here is S, and I can have my long-term equilibrium conditions, which is a large number of equations, and so what is the results in terms of only one variable, which is this S, whereas D is the stress direction. It is the collection of all those lambdas and mu's. And you can see in this case that I can find the maximum power I can transfer from area A to area B. For instance, if I increase the load in area B and I increase the load also in area C, I get another limit. And if I increase the generation at area B and the generation at area A, I get also another limit. So assume that I increase the generation at area B, and I increase the load in area A, I get the maximum power transfer from area B to area A. So this is a multi-dimensional problem, but I can see it in a single dimension, which is the direction of the stress. All right, I'll leave the rest for you in case you want to ask, and I will give you also a number of references here where you can see further reading. And with this, I'm open to questions because I don't want to take any more time from you. Any questions?
Okay, thank you so much, Doctor. Guys, if anyone has any question, you can just raise your hand and open your. If you guys have any. Dr. Muhammad Arnaout has a question. Please, Doctor.
Okay. First of all, thank you, Professor, for your presentation and for this rich presentation. In fact, my question regarding the complex power system or real power system, as you know, from the slides, you take first of all as a simple way 2 buses, and then you compute all the equations. But in real case, how can we manage a large power system? How can we assume, or how can we detect some instabilities, and what is the solution for these instabilities in real case?
Okay, well, let's try to. Can you see the slides now?
Yes.
What we usually do, we have a number of differential and algebraic equations. Typically, the algebraic equations are the load flow equations. If we have what we call short-term dynamics and we want to do long-term stability, we can assume that we have an equilibrium condition for this dynamic. So usually what we do, we have a set of conditions, which is the short-term equilibrium conditions and the load flow equations. This is a set of algebraic equations that will give you the condition of the system, and we allow the system to evolve in the so-called long-term time scale, for instance, using only the discrete dynamic of the tap changers, okay? So one way to analyze the system is we can take all these equations. I have more than I wanted to present. We can take all these equations. So you see here, I have a set of equilibrium equations, and I can solve this problem either with optimization to get the S that will, to find the maximum S, the maximum stress, or I can stress the system by increasing S and monitor to see the stability of the system as it goes along, okay? So in this case, I have, let's say, it's not, let's say, as simple as the radial system, but I can get something like a PV curve in the multi-directional, in the multi-load system, but this will be the stress, not P, this will be the stress. So I can see where is the maximum power transfer, the maximum value of S as it evolves along. And as it evolves along, it can go beyond the maximum stress because all I'm changing is the load consumption. So if I have a modeling of the load, like for instance, constant admittance, I can always find a solution, and I can plot this curve with continuation power flow or by simulation, assuming voltage-dependent load. I can see this value as. Suppose now that my consumption, expected consumption, is this line here, which is more than I get. I have an idea of the minimum reduction of consumption that I need to restore stability at point C. So this is roughly the way we monitor or we analyze offline voltage stability during in a real power system using the load flow equations, the equilibrium equations for generators and motors, and assuming a direction of stress.
Thank you.
I
Thank
try
you.
to make a short answer, but it's not always easy.
Yeah, because as you know, the domain of stability is very huge and very complex. So
yeah, and especially for non-linear systems, a very
yeah,
little thing you can do.
yeah.
So I was
Okay, thank
asking
you.
everyone if they have any other question in the chat box. I think no one has questions. Before concluding, Dr. Muhammad Arnaout, we'd love to hear a small word from you, please.
Okay, thank you, Professor, for this presentation and for sharing with us your knowledge about this domain, and hope also to see you soon in Lebanon after the pandemic. Thank you for every student and every professional and every doctor who attend this presentation, and special thanks also for the IEEE student branch LIU to organize this event, and for the IEEE joint chapter presented by our president Abdullah Qasim and ex-president Dr. Nazih Mbayed. Thank you a lot, and see you soon, inshallah.
Thank you also, and I'll be glad if anyone has any question, they can also, I mean, for more detail, can send me an email, and I'll be glad to answer. I have made available the PDF of the slides, so you can share for those interested. And I guess you have my email, so you can also always, and I'll be glad to be able to travel and meet some of you.
Thank you so much. Same feeling. Dr. Abdullah, would you like to add something?
No, just to say, Afghanisto πολύ.
Παρακαλώ.
Παρακαλώ. Okay. Καλησπέρα.
Γεια σας, γεια σας.
Γεια σας.
Have a nice evening.
Yalla, bye.
Καλό βράδυ.
Thank you.
Have a
Thank
nice
you.
evening, everyone.
Bye-bye.
Bye.
Bye-bye. Thank you so much.